Okay, good morning again. Welcome back to this lecture series. And we are going to move on to, I think, our fifth lecture on the fundamentals of electrochemistry, electrochemical sensors rather. We're going to go with the electrochemical sensor fundamentals. So this electrochemical sensors requires so-called solid electrolytes or superionic conductors, abbreviated as SiC. So if we look at insulating ceramics, where the conductivity is very low, these are primarily Siemens per centimeter unit. Conductivity is very low in typical insulating ceramics. The solid electrolytes have conductivity exceeding 10 to the negative 5 with an ionic transference number. So this transference number represents percentage of conductivity contributed by movement of ionic species. So the ionic transference number is practically 1, meaning 100% of the conduction comes from transport of ionic species. So the transference number is defined as the transference number of species I is conductivity contributed by that particular species compared to the total conductivity coming from all the species. So if you sum up all the transference number, obviously it should sum up to 1. So total conductivity is defined as sum of the conductivities of coming from ionic species, electronic species, and so on. And you can see that the electric conductivity is controlled by 2 critical parameters. One is the concentration of the charge-carrying species, how many of them are moving, and how fast they're moving, their mobilities. So since the mobility of electron and hole are typically larger than the mobility of ionic species, for superionic conductors, the concentration of charge-carrying species has to be dominant to get substantial ionic conductivity. So if you do some comparison of normal ionic conductor versus superionic conductors, then you can see superionic conductors is referred to as fast ion conductors, solid electrolyte. These are, by the way, not superconductor, which are superconductors are electronic conductor, but we are talking about superionic conductor. So don't mix up with superconductors. So superionic conductors, they are ionic conductor, meaning the ionic conductivity is much larger than electronic conductivity. In other words, ionic transference number has to be practically 1. So if we do some comparison, at room temperature, for example, a normal ionic conductor like sodium chloride has a conductivity of the order of 10 to the negative 20 Siemens per centimeter. On the other hand, rubidium silver iodide, which is a superionic conductor, has electrical ionic conductivity of the order of 1 Siemens per centimeter. It's a huge difference. You can see that this group of materials compared to normal ionic conductors deserve special attention. So here's a list of the various types of superionic conductors or solid electrolytes. So there are fluorine-based materials, which is anion conductor. Fluorine, negative fluorine is the ionic species, transporting species. And there are silver-based materials, where silver is the transporting species. Oxygen ion conductor based on stabilized zirconia type material that we'll talk about. Sodium beta alumina type, Nasicon type sodium ion conductor. And then lithium-ion conductor, LiPon, and a lot of other lithium conducting materials. And then there are a series of proton conductors that can conduct protons, hydrogen plus. So if you look at the kind of Arrhenius plot, logarithm of ionic conductivity times temperature versus 1/T, you can see here are the various types of material. Silver iodide, which is a silver ion conductor, it goes through a first order transition from low temperature insulating material to high temperature superionic conductor. This is the rubidium silver iodide, sodium beta alumina, stabilized zirconia, fluoride type material, fluorine ion conductor, and compare all this conductivities of these materials. These are superionic conductors compared to normal conductor like sodium chloride. And you can see that as you approach a low temperature, so to the right is the low temperature, they are gradually diverging. Their difference in ionic conductivity values differ by several orders of magnitude. Whereas if you approach the high temperature to the left, it looks like they're going to converge. So if you look at their high temperature behavior, there's not much substantial difference in their conductivities, but it is the room temperature or low temperature conductivity that actually distinguishes this group of superionic conductors. That's characteristic of superionic conductors. So, does superionic conductor accompany phase transformation? That was one of the questions that was asked in terms of what makes a superionic conductor superionic. So this is a historical type of analysis. So for a long time, it was believed that for a given material to show superionic conducting behavior, you need to have at least first order transformation, like in silver iodide, where it goes from low temperature beta silver iodide, which has a Usteig type structure, to high temperature alpha silver iodide, that is body-centered cubic type arrangement. And this transition temperature is around 149 degrees or 150 degrees. And around that transition temperature, if we look at the logarithm of conductivity, the 3 orders of magnitude and associated volume change, first order transition. And then they discovered so-called fluoride type material that showed that there is no first order transition, but there is second order transition. This lambda type behavior and specific heat, for example, is continuous lambda behavior and specific heat. So they said, okay, if you don't need first order transition, you need probably second order transition. And I will show you some of this data. You can see that there's the silver iodide that goes through a first order transition, associated with structural change, leading to volume change. And then the lead fluoride material, there's a continuous change in conductivity. And this is associated with water disorder type transition, going from a disordered state at low temperature, the watered state at low temperature to disordered state at high temperature. It goes through a water disorder transition that shows discontinuity in something like specific heat, second order transition. Then they discovered the beta alumina type materials that does not show any type of transition. So then the question is, what is then the criteria that makes a material superionic conductors? So I'm going to specify some conditions, and hopefully it will make sense to you. First of all, it says the lattice must include more sites then ions to fill them. So there are some empty sites for ions to fill. So that's criteria number one. If all the sites are filled, then no diffusion can happen. So the lattice must further be such that ions can easily hop from their site to nearby empty sites. So this has to do with the low migration energy, that even though there is an empty site, some energy is required to access those sites for ionic motion. So the activation barrier to reach those sites has to be low, meaning that ion should be sitting in shallow potential. And then the third criterion, which is a very important criterion, that there must be connected pathway through the lattice. Otherwise, there can be large local jump rates without significant DC electrical conduction. If you're looking for DC electrical conduction, the ions that move from one electrode all the way to the other electrode will contribute to DC conductivity. But if the ions are locally moving, makes few jumps, and then don't then get into a deep hole and cannot move any further, they are not going to contribute to DC conduction. So this criteria is an important criteria. And I'm going to illustrate these in an example taking alpha silver iodide. So alpha silver iodide has this body-centered cubic arrangement of iodine. So these are the iodine. There are 2 iodine per unit cell. There's a body-centered cubic. And for this 2 iodine per unit cell, there should be 2 silver. And for those silver, there are all kinds of different types of sites available in that unit cell, cube unit cell. There are so-called octahedrally coordinated sites shown as solid squares on the face of the cube. 6 of those, since there are 6 faces, these will count as 6 faces, and these will count as other 3. Okay, so there are a total of 6 octahedrally coordinated sites per unit cell. There are 12 tetrahedrally coordinated sites shown as solid circles. On each face, there are 4. There are 6 faces, and each face is shared by 2 unit cells, so there will be 12 these sites. And then in between the tetrahedrally coordinated sites, this open circle, there are 24 H sites. So these are different types of sites available for silver to fill in. 2 silver per unit cell, with so many different types of sites. So clearly many of the sites are going to be empty, which is criterion number 1. Then if you look at the electron density map of one of these 2 faces. So the electron density map is you send an electron beam, and then that electron beam is scattered by silver, for example. So these are characteristic scattering map, if you wish, of this coming from the silver ion. So this electron density map, if these contours are closely packed, that means high density, high concentration. And if they're loosely packed, then the low concentration. You can see that this is a face of a cube, and so this is the octahedrally coordinated sites in the center of that cube face. And these are the 4 tetrahedrally coordinated sites, so-called D sites. And you can see that most of the silver resides on the tetrahedrally coordinated sites. There is some silver in this, octahedrally coordinated sites, and there are some silver in the H sites, and so on. But remarkably, this electron density map shows that they are diffused. So the silver is not sitting necessarily around that tetrahedrally coordinated sites. So they're all over this place. So this shows this diffusedness in silver mapping. Silver density mapping shows that silver is almost everywhere. And this is an indication that the silver is sitting in, if you think in terms of electrical potential, they're sitting in very shallow potential, so that silver can wobble around over larger distance. That's why the silver mapping shows that this diffuse type distribution in the silver mapping. So this is an indication that the activation barrier, since it's sitting in a shallow potential, it has to overcome very shallow activation barrier. In fact, the migration energy for silver in this material is of the order of 0.05 electron volt, 0.05 electron volt. Not a very deep potential, but very shallow potential. And to give you a sense of electron volt is the amount of energy to take an electron across 1 volt. So if you think about room temperature, which is 300 Kelvin, that corresponds to about 25 milli-electron volt. So 0.05 electron volt cannot be overcome at room temperature, but you don't need much thermal energy to overcome that barrier. So this fulfills the second criterion, that not only you need a lot of empty sites for ions to fill, but those empty sites should be easily accessible. And we can see that in this diffused nature of the silver mapping that gives an indication of shallow potential. And then if you do a cartoon, then you can see again, I'm showing this silver electron density map, octahedrally coordinated sites, tetrahedrally coordinated sites. And this diffuseness shows that these are actually connecting from one phase to the neighboring phase and so on. And this shows the interconnectivity throughout the lattice, which is the third criterion, that if this pathway is discrete and they are not interconnected throughout the crystal structure, then they wouldn't contribute to the DC ionic conductivity, which was the third criterion. You can see in a material like this, the iodine sublattice is very rigid, but the silver sublattice is highly disordered. And this highly disorderedness gives this indication of shallow potential, as well as this connectivity or connected pathway throughout the lattice. And I'm not going to go through the detail in beta alumina. It's kind of another superionic conductor. Beta alumina structure can be viewed as a layered structure. So you have basically a layer of spinel type arrangement, spinel structure. So there are 4 layers of aluminum and oxygen in the spinel block, then conduction plane, spinel block, and then conduction plane. So it's a layered structure. I'm basically showing schematically the 4 layers of aluminum and oxygen in the spinel block, and conduction plane, where you have your transporting species. So this would be for sodium beta alumina. This would be a sodium, this would be oxygen in the 2-dimensional conduction plane, and then spin block, conduction plane, and so on. So the conductivity happens on this 2-dimensional layer. So unlike silver iodide, which is a 3-dimensional ionic conductor, beta alumina is a 2-dimensional ionic conductor. And it has implication on processing of the material. So you want to really create a microstructure which is textured with C-axis in the grains more or less aligned. So the conduction from grain to grain can happen on the conduction plane, and there is not a big, huge mismatch from going from grain to grain. Anyway, it's too much detail that I'm not going to go through. There are two types of beta alumina structures, so-called beta alumina and beta double prime alumina, where unit cell is bigger and the types of sites available for sodium. So there are 3 different types of sites available for sodium on the conduction plane. Those sites become equivalent in beta double prime alumina. So beta double prime alumina is a little slightly better conductor than beta alumina, but they're equally good conducting materials. And the activation barrier for this material is of the order of 0.17 electron volt. Not as good as silver iodide, but 0.16 electron volt is not too bad either. The other type of superionic conductor is the so-called stabilized zirconia. Zirconia oxide, it can be actually sort of synthesized from naturally occurring zircon, and zirconium oxide has 3 distinct phases, so-called monoclinic phase, which is stable up to 1170 degrees C, the tetragonal phase that is stable up to 2370 degree Celsius, and the cubic phase, the high temperature phase, which is the fluoride type structure, which is stable up to 2680 degrees Celsius. And there is a transformation between monoclinic and tetragonal phase. It's a diffusion lace transform, shear process. There's a large volume change, and so the material actually shatters sometimes because of large volume change, cracks. But cubic phase is the superionic phase, and it can be stabilized down to room temperature by doping. And you can see that if you look at the zirconium oxide, yttrium oxide binary phase diagram, you can see that there is a huge solubility limit of yttrium into the cubic zirconium phase. And you can stabilize that cubic phase at low temperature by doping. And what the doping does is you can dope, if you dope zirconium with yttrium oxide, and this is using Kroger-Vink notation for point defects, that you substitute yttrium on zirconium site, and for 2 of this substitution, you have to create an oxygen vacancy. So in yttrium, yttria-doped zirconia, known as yttria-stabilized zirconia, or you can do calcium-stabilized zirconia. Same thing for each substitution. In this case, you will create an oxygen vacancy. And in this cubic material, this oxygen vacancy is the vehicle that makes this material oxygen ion conductor that is used as a superionic conductor, solid electrolyte in many of the gas sensors and fuel cells and so on. So with that little background, let me move on to electrochemical or so-called potentiometric type of sensors and some of their basics. So these sensors are created based on so-called electrochemical galvanic cells. And I give you some references. And if you look at the conductivity, log of conductivity as a function of oxygen partial pressure, for example, or in alkali halide, this can be partial pressure of chlorine or fluorine or bromine and so on. But for oxide, this is primarily oxygen partial pressure. So you can see, you can get, for example, in stabilized zirconia, for example, you can get N-type behavior and very low oxygen partial pressure. Then it can go through mixed ionic and electronic conduction, and then to ionic conductivity, where the conductivity does not depend on PO2. And then moving on, when you move to the high pressure side, you go through mixed ionic and electronic conduction, eventually to P-type conduction. So you can see this PO2 range will define the range of operation of your ionic conducting material. And in stabilized zirconia, for example, if you do the plot the ionic transference number and very low PO2, you get electronic conduction. So the ionic transfer number is going to be 0. And it moves through the mixed ionic electronic. So you can see that now the ionic transference numbers will keep on increasing. And as soon as you enter this ionic regime, then ionic transfer number become 1. Then it keep on decreasing as you move to the P-type regime, with the mixed conduction to completely P-type electronic conduction, where ionic transfer number becomes 0. So again, you can see in here, this range will give you the stability range of the electrolyte that can be used in a galvanic cell. So this kind of analysis defines the range of stability of the material and the range of application of the material as an electrolyte. So if you look at the Kroger-Wing, again, Kroger-Wing diagram for stabilized zirconia and its corresponding electrical conductivity as a function of PO2, it looks something similar to what I already described. So this is the useful range. You want to be a little bit away from that boundary of the mixed ionic electronic range, so that you ensure that you're going to operate that material in the ionic range. Fortunately for stabilized zirconia, be it calcium-stabilized or yttria-stabilized zirconia, this range happens to be a very large range of PO2. So let me move on to the galvanic cell-based measurement. So what you're trying to do is you have an electrolyte, which is an ionic conductor, and you have an anode and a cathode, 2 electrodes. And if you create different concentration of your mobile species at these 2 different electrodes, you can measure an EMF, electromotive force, that will be non-zero. Okay? And that electromotive force can be given by this so-called Nernst equation. That electromotive force that you measure will be proportional to the logarithm of activity ratio of the mobile species between the 2 sides. You can see that activity, which typically will be related to the concentration of that species. So the idea of galvanic cell type measurement is that you measure EMF and you will use one of this electrode as a reference. And for the reference electrode, you know the activity. And with respect to the known activity, you figure out the unknown, which is the sensing side. With respect to the known reference, you detect the concentration on the sensing side by simply measuring the electromotive force by connecting the 2 electrodes to a multimeter. So that's the principle based on Nernst equation. And in a galvanic cell, you have chemical reaction happening on both electrodes, which are known as so-called half cell reactions. And the delta G of the overall reaction, which is the, if you add up the two half cell reactions, you can get the overall delta G of that reaction is related to the electrical work in the galvanic cell, which is given by negative number of units of electron, number of moles of electron being transferred to the external circuit that gives you the EMF. And F is the Faraday constant. And the delta G is nothing but delta mu, chemical potential difference between the two electrodes. And the delta mu can be related to RT logarithm of the activity ratio. So again, you can see that this N is same as the number of moles of electron that you're transferring to the external circuit. So knowing one of these activities, you can figure out the other side by measuring EMF. So that's the basis of galvanic cell type measurements. So if you look at the bulk electrochemical type sensors, the so-called, there are equilibrium type. So-called type 1, where you're, so this is your electrolyte, which is an AB compound. And let's say A is the transporting species. Okay. And if you're trying to detect a gas environment, which is matches exactly with the transporting species, then it's type 1. So for example, you can use yttrium zirconia, which is an oxygen ion conductor. You're transporting a species is oxygen, and you're trying to detect oxygen. So this is direct coupling. So the detecting environment couples directly with the transporting species, and hence type 1 is inherently selective. And there are so-called type 2, where you have an AB compound as your electrolyte, and you're trying to detect B that couples not with the transporting species, but with the conjugate. So for example, if you're using sodium sulfate as SOX type detection, sulfur dioxide or sulfur trioxide, for example, and you can use an electrolyte where sodium ion is the transporting species. So your gas environment does not interact directly with the transporting species, but it interacts with the conjugate sulfate ion in the compound. So there's indirect coupling. So when you change SOX, sulfur dioxide environment, it interacts, chemically interacts with this B species in the electrolyte and changes the activity on the side. So with respect to the fixed reference, you detect the target or the measuring environment by this indirect coupling. And there is type 3, where basically you can see there is an AB compound, which is your electrolyte, and you're trying to detect environment containing C component. So C doesn't have any correspondence with either A, which is the transporting species, or the conjugate B. So it actually couples through an auxiliary phase, known as the auxiliary phase or sensing side, or whatever you want to call it. And it couples with the C component in the auxiliary phase that changes the activity A, and that's what you're trying to detect through your EMF measurement. So you change C, it changes the activity of A on the auxiliary phase, that couples with your electrolyte. So the beauty of this type 3 is that you can use the same electrolyte. So for example, you can use beta alumina, for example, sodium beta alumina, And you can use sodium sulfate to detect sulfur dioxide as the auxiliary phase. Or you can use sodium nitrate as the auxiliary phase to detect nitrogen oxides. Or you can use sodium carbonate, same electrolyte. You don't have to change electrolyte, but you can change the auxiliary phase to couple with the detecting phase. So you can use carbonate to detect CO2. So this is a really very attractive device. And then there are non-equilibrium type, mixed potential type, and amperometric type that I'll talk about later. So just to show you some examples of these different types of equilibrium type. So type 1 is the so-called oxygen sensor. To use it, stabilized zirconia as an oxygen ion conductor. And platinum is the lead wire that you're using to connect to the multimeter. And you have a reference side where you maintain air as the reference. And the unknown side is what you're detecting through measurement of the EMF of this kind of cell. If you look at the little bit detail of this HAP cell reaction, on the air side, reference side, it grabs oxygen molecule, combines with 4 electron to create the 2 oxygen ion that will move from the left to the right. And this is the sensing side. So, the reverse reaction will happen on this side, where this 4 electron will actually move through the external circuit that gives you the EMF. And so the actual design of that oxygen sensor will look like something like this. So you get yttrium zirconia tube in tubular form, and then you trap air inside. So the inside air becomes the reference side, where you know the PO2, oxygen partial pressure. So with respect to that known reference, you can detect the unknown, which is the outside. And this oxygen sensor comes with a protective layer, stainless steel casing. And this gets injected or inserted into the automotive exhaust. Okay, so you're trying to detect the unknown environment with respect to the known reference, which is air, and you seal this air. So it has to be gas tight sealing at this end. And again, if you measure EMF by connecting inside versus outside, it's painted with platinum inside, painted with platinum outside, and you connect inside versus outside. The EMF signal will be proportional to the logarithm of the partial pressure of oxygen between the reference and the unknown. So by knowing this, the measurement of the EMF will give you the unknown value. And that's what the oxygen sensor is doing in your car. So here is some design. Again, the stabilized zirconia tube, painted with platinum inside, painted with platinum outside, and you're measuring the EMF by connecting inside versus outside. And this is in the exhaust environment. So here's another design. You can see, again, the stabilized zirconia tube. Air is inside, platinum painted inside, platinum painted outside, and you connect inside versus outside. So this is designed in a way that it can be inserted into a spark plug type port. So there is a port for this oxygen sensor, which is known as the lambda sensor. And the name lambda comes from this response from the sensor. If you look at the response in terms of millivolt across the stoichiometric mixing ratio of the air to fuel mixing ratio by weight, for a stoichiometric mixing, it would be 14.7 by weight. Across that stoichiometric ratio, the sensor signal changes by many orders of magnitude. So if the mixing ratio drifts slightly to the right or slightly to the left, the sensor immediately recognizes that it's drifted. And you can see the shape of the signal looks like a Greek letter lambda, and hence this is known as the so-called lambda sensor. And this works like a switch because of the huge difference in the signal as the mixing ratio slightly deviates to the right or to the left. So this sensor is actually always monitoring that signal of the sensor and sending a signal to the actuator. If it drifts, it tells the actuator to remix so that the mixing ratio always is maintained at the stoichiometric ratio. So here is an actual oxygen or lambda sensor. Here is your stabilizatory tube that is painted inside and outside with platinum. And this is covered with this stainless steel housing with the hole that will allow the exhaust gas to come in. And you can see it's connected to the onboard electronics. And so this is the real oxygen sensor. So this is the sensing element. It's very inexpensive. Automotive industry buys one of this for a few dollars, $2 to $3. The other type 2, you can see you can make a SOX sensor. SOX type sensor, sulfur dioxide type sensor or sulfur trioxide type sensor with the silver sulfate as the electrolyte and the reference electrode as silver, where the activity of silver is 1, which is fixed. And then, you can measure the EMF between the 2 electrodes, and the EMF signal will be given by the 2 half cell reactions added together will give you the overall reaction happening in the cell. And the EMF can be related to the delta G of formation of silver sulfate that you can look up, Faraday constant, and the signal will depend on both the partial pressure of your detecting gas as well as partial pressure of oxygen. So if you're trying to use the sensor in an environment where oxygen concentration changes, then you will need to employ an oxygen sensor along with the SOX sensor. And you can see that this is type 2 because the change in the gas environment is coupling not with the transporting species, which is silver, but it's coupling with the conjugate sulfate ion material. Here's an example of type 3, where there's a reference electrode. You can see the galvanic cell structure, so you can use macicone, which is the compound shown here, which is sodium ion conductor. Okay? And you can use this mixture as the reference electrode, that sodium zirconate and zirconium oxide mixture that fixes the activity of sodium on this electrode. That activity doesn't change even though you change NOx. And then auxiliary phase is used as sodium nitrate. And as you change the NOx environment, the activity of sodium on that material changes. Activity on this side. You're measuring the signal. You can see the half cell reactions on the 2 electrode, and then EMF is given by this formation energy of sodium nitrate and sodium zirconate. These are, you can look up the thermodynamic database, and then the signal depends not only on the NO2 partial pressure, but it depends on PO2 as well. So if your oxygen environment is changing, along with the NOx sensor, you will need an oxygen sensor as well. But the beauty of this type 3 is that if you want to use the same electrolyte and want to detect CO2, for example, then you can use sodium carbonate as the auxiliary phase. Or if you want to detect SOX, for example, you can use sodium sulfate as the auxiliary phase and use the same electrolyte. Let me spend a little bit of time on the so-called mixed potential type, non-equilibrium type sensor, where you can take something like stable zirconia and then use two electrodes, one platinum and gold, and you can measure the signal, so-called mixed potential between these two electrodes in an environment like CO2 and oxygen and CO, where you can look at the logarithm of the current versus electrode potential in a device like this that will show you the behavior will look something like the gold electrode, the oxidation reaction, CO oxidation reaction will have this characteristic, whereas on the platinum, the CO oxidation will have different characteristics. But the oxygen reduction reaction on both electrodes are very similar. So oxygen reduction reaction on both gold and platinum will generate this current that is generated from the oxygen reduction reaction, generate electron. But the idea is on this two electrode, the CO oxidation rate is different. It creates these different slopes. So you can measure the delta E, which is this mixed potential, and mixed potential is taken as current is equal from the reduction reaction and oxidation reaction. On the gold electrode, it's right there, and the platinum is right there. And the idea now is that on a sensor like this, here, some detail you can see, oxygen reduction reaction will lead to this oxygen reduction current, and the CO oxidation rate will generate the CO oxidation current that you're measuring and plotting in here. But the beauty of this is that you can change your electrode. So let's say I put rhodium or some high temperature oxide catalyst material that will change the CO oxidation reaction, meaning that will change the slope. So depending on the oxidation reaction rate, the slope of that curve will change. And that will change the magnitude of delta E, signal that you're measuring. So you can modulate the signal to increase the sensitivity or decrease the sensitivity. But the higher slope means the reaction rate is going to be different, So you can actually study by looking at this kind of mixed potential type behavior. You can actually choose your catalytic material, whether a slowly reactive catalyst or highly reactive catalyst. The other type is the so-called amperometric or limiting current type sensor. Remember, in the type 1 oxygen sensor, since the signal is proportional to logarithm of the PO2 ratio. So if the PO2 that you're trying to monitor, let's say, continuous change in oxygen concentration. So the ratio, so for example, if you're trying to distinguish between 21% oxygen in air versus an environment, let's say 15% oxygen. So if you take the ratio of this 0.1 atmosphere versus 0.15 atmosphere, the signal is not going to be large. So that while that Type 1 oxygen sensor is wonderful for automotive exhaust monitoring and maintaining the air-to-fuel mixing ratio around the stoichiometric level. It's not going to be very good for continuous monitoring. In that case, you can use this amperometric or limiting current type sensor, which is designed by, again, you take an electrolyte, you twist a zirconia with 2 platinum pads printed, and one side, well, platinum on one side, you isolate with a hole, tiny hole. And then if you measure the IV of this device, when you apply voltage and measure current, the current will go like this. But the current will increase as you increase the voltage. This part is really measuring the resistance of the electrolyte, the resistance coming from the motion of oxygen ion through the electrolyte. And then if you exceed certain voltage, and by applying voltage, by the way, you're pumping oxygen from one side to the other. You know, if you take an oxygen ion conductor like it twist of zirconia, apply voltage, you can actually pump oxygen from one side to the other. So that's what you're doing, pumping oxygen through this membrane, through this electrolyte. And then it says that current increases and then it remains constant. So what you're doing, that by increasing the voltage, you keep on increasing the pumping rate. So when the diffusion rate from the ambient through this hole exceeds, the pumping rate. When the pumping rate exceeds the diffusion rate of oxygen coming from the sensing environment into this chamber, when this pumping rate exceeds that diffusion rate, then current is not going to change. So whatever is coming in, you are immediately pumping it out. So the chemical potential of oxygen here remains constant. So the signal doesn't change up until where you exceed voltage, applied voltage to so high that your electrolyte decomposes, meaning that electrolyte now goes into the electronic conduction regime. So it actually becomes an N-type semiconductor at very high applied voltage. So this limiting current is operation range is this voltage range, where you're measuring this limiting current, and you can relate this limiting current to the oxygen content in the measuring environment. And if you change the PO2, you will see that this limiting current will change, keep on changing. So that's the calibration curve for this kind of sensor. And you can design this amperometric sensor by making a very well-defined hole. If you make this kind of sensor with a single hole separating this chamber, if you plot the limiting current versus negative logarithm of 1 minus mole fraction of oxygen, you get this linear behavior. So that's your calibration curve. So you measure the limiting current and you figure out the oxygen content. Or you can make separate this platinum side by putting a membrane made of nanoparticles, for example. If you use monodispersed, mono-sized nanoparticles and make a coating, you will have well-defined pores through which oxygen will be pumped in. And in that case, from a device like that, if you plot current, limiting current again, versus mole fraction of oxygen, it will give you a linear correlation. Again, the idea is that you measure the limiting current and you can figure the oxygen content. So this device is a good one. And with that, I'm going to stop here Thank you for your attention, and I will see you in the next lecture.